Yeah, good morning all. So in this video, I will be discussing on computer networks course. The topic is MAC protocols, that is media access control protocols. So there are three categories of protocols, that is the random access protocols, controlled access protocols, and channelization protocols. In the random access, we have Aloha, CSMA, that is carrier sense multiple access, carrier sense multiple access with collision detection and collision avoidance. These are the four categories of random access protocols. Then we have controlled access protocols. There we have reservation, pooling, and token passing. And lastly, we have channelization protocols, that is FDMA, TDMA, and CDMA. That is frequency division multiple access, time division multiple access, and code division multiple access. So these MAC protocols are meant to control the access of multiple systems whenever they are going to access at the same time. So we are going to control the media. So the random access protocols will help in controlling the congestion by 10 to 20%. When it comes to controlled access, it can control up to 80 to 90%, and the channelization protocols can control 100% collision. Thereby, we can achieve the throughput 100%. So today we will see the first category of protocols, that is random access protocols. In that we will see what is Aloha and what are its types. Okay. So there are two types of Aloha techniques. Since it is the random access protocols, so the chances of collisions will be more. So in random access, any station can transmit the data at any time. There is no restriction. That's why there are more chances of collisions, and the throughput will also be very less. So in Aloha, we have two types. One is known as pure Aloha. The other one is slotted Aloha. Okay. Let us see both today. So what is pure Aloha? Pure Aloha is an unslotted, there is no slotting technique. It is a decentralized and a very simple to implement. As I told you, in pure Aloha, the stations can simply transmit frames whenever they want data to send. So the problem is whenever there are multiple systems are free to transfer the data, then at the same time they will transfer the data. Thereby, there are more chances of collisions. Okay. It does not check whether the channel is busy or free before transmitting. So if the station is free, it will transmit. They will not check whether the channel is free or not. Because of that only, there are more chances of collision. So here you can see one small example. There are totally 4 stations, station 1, 2, 3 and 4. Station 1 is sending 2 frames, that is frame 1.1 and 1.2. Similarly, station 2 is sending 2 frames. Station 3 is sending 2 frames, and station 4 is also sending 2 frames. Totally, 4 stations have transmitted 8 frames. In that, if you see clearly, the second frame of station 1 and the portion of first frame of station 2 is collided. Similarly, some portion of first frame of station 2 and also the first frame of station 3 is also collided here. I have shown in some shaded color. Similarly, almost some portion of frame 2 of station 1, some portion of frame 1 of station 2, and some portion of frame 1 of station 3, as well as some portion of complete frame, first frame of station 4 is also collided. Similarly, here also there is some collision between second frame of station 2 and also second frame of station 4. So if you observe clearly, so these are all we call it as collision duration, the time where the collisions are occurred. So if you observe clearly here, totally 4 stations have transmitted the 8 frames. In that, only 2 frames are not collided. Remaining 6 frames are collided. So the percentage of successfully transmitted frames or the frames that are not collided is only 10 to 15%. So that's why I told In pure Aloha, there is more chances of collisions because of any station can transmit the data at any time. They will not check whether the channel is free or not. Okay? So this is the procedure for pure Aloha protocol. So here we should remember few terminologies like K is nothing but number of attempts. TP is known as maximum propagation time. TFR is known as average transmission time, and TB is known as backoff time. Regarding all these, I've already explained in the previous lecturer. You can just watch once. Okay. So, for examples here, there is one station 1 and station 2. If station 1 wants to transmit or it wants to send data to some station 2 or any other station. So that's what first time the station is transmitting the data. So here you can see the K is 0. The station has sent a frame to send. Okay, the station has frame to send. So it is almost to send. So first time it is sending. So the number of attempt is 0. So now you can send a frame. Once the frame is sent, so already we know that the frame is attached with RTT. We call it as a round trip time. RTT is known as the time taken to transfer the data to station 2 and also getting back the acknowledgement from station 2 to station 1. That we call it as round trip time. So here you can see once the frame is set, you have to wait for that time, round trip time. Here we are calling it as 2 times TP, 2 times the propagation time you have to fix. So you have to wait until that time before transmitting the next frame. So within that time, if the acknowledgement is received from the station 2, then we can say the packet is successfully received. So within that time, if the acknowledgement is not received, so the protocol will think that the packet might be lost or it is corrupted. So it will go for second attempt. So K equal to K plus 1. So here, whenever you are going to the next attempt, it has to check the attempt number. So the maximum attempts you can go is not more than 15. So if it is second attempt, no problem. If it is third attempt, like that, up to 15 attempts you can go. So 15th, after 15th attempt, then the protocol will remove that node from the network. Okay. So think that we are going for second frame. So it will allocate some random number R, which is between 0 and 2 power k minus 1, where k is nothing but number of attempts. Based upon the number of attempts, it will allocate some time to wait before transmitting the or before retransmitting the same frame. So that time we call it as TB, we call it as backoff time. Just like once if a student is failed in the regular exam, he has to wait for the 1 or 2 months to get the arrear exam. Here also same thing. They have to wait for some time. That is we call it as TB, backoff time. That time after waiting, then he can go for sending for next attempt. That is K equal to K plus 1. Again, he will send the frame. Again, he will wait for some round trip time. Again, he will see the acknowledgement. If the acknowledgement is got within the specified time, then the packet is successfully sent. Otherwise, go for the second attempt, third attempt, like that. You can go until 15 attempts maximum. Okay. So in this way, the pure Aloha will work. So hope you have understood. So here is a small example how or how to calculate the overall throughput of pure Aloha. So here is the question. A pure Aloha network transmits 200 bit frames on a shared channel of 200 kbps. Okay. There is one channel with 200 kilobits per second capacity and it can transmit 200 bit frames. Okay. So what is the throughput of this system? Okay. If here you can see all stations are sending data together, just like I have shown in the diagram. So if the stations produces 100 frames per second, what is the throughput? Means how many frames will successfully transfer without any collisions? So if it transfers 500 frames per second, what will be the throughput? If it transfers 250 frames per second, what is the throughput? A simple example. First, let us see what is the frame transmission time. So the frame transmission time is nothing but 200 bits per bit frames at 200 kbps. So just you divide it, 200 by 200 kbps, you will get 1 millisecond. So that is the frame transmission time. TFR. Once you calculated TFR, then you need to calculate the load of that channel. So if the system creates 1000 frames, sorry, okay, if the system creates 1000 frames per second, but our channel is working at a frame speed of 1 millisecond. Okay, that you should keep in mind. So that's what if the system creates 1000 frames per second, okay, then how many frames it can send in 1 millisecond. We are working with 1 millisecond now. So just you write 1000 by 1000. So you will get 1 frame per millisecond. Milli means 10 power minus 3. So 1000 divided by 1000, you will get 1. So here the load is 1 now. So in this case, so the formula to calculate the throughput in pure allow is S is equals to G into e power minus 2G, where G is nothing but load, which is nothing but 1, and E is nothing but Euler's number, which is equals to 2.718. So just to calculate that, S is equals to G into e power minus 2G, then you will get S is equals to 0.135, which is nothing but 13.5% of frames will be successfully transferred. So this means that just to multiply 1000 into 13.5%, you will get 135 frames. So if you transfer 1000 frames per second, then out of 1000 frames, only 135 frames will be probably survive, or without collisions they can exist. So the probability is only very less, only 13% packets will move without collision. Okay. Similarly, if 500 frames per second is sent, so if the system creates 500 per second, then the load will be 500 by 1000, okay, which is 1 by 2. So the load is half. So in this case, just substitute instead of G equal to 1, you can substitute G equal to 0.5. Then you will get 92 frames. So out of 500 frames, 92 frames will probably survive without any collision. Similarly, 250 frames you are sending now, just to write 250 by 1000 because we are dealing with milliseconds. Then you will get 1 by 4. So that is what the load. Just substitute G value as 1 by 4, then you will get the overall throughput is 38. So out of 250 frames, 38 frames will successfully transfer. So here the percentage is very, very less, within 20%, the throughput we are achieving. Okay. So this is a simple example of pure Aloha. Now let us see about slotted Aloha. Okay. The name itself tells slotted means time slots. So in slotted Aloha, the time of the shared channel is divided into discrete intervals called slots, just like our timetable, 9 to 10, 10 to 11, 11 to 12, like that. We are dividing the complete channel in terms of slots. So the stations are eligible to send a frame only at the beginning of the slot, and only 1 frame per slot is sent. Very, very important. So only the station is allowed to send at the beginning of the slot, not in between of the slot. For example, if the slot is from 9 to 10, so any station can transfer only at the beginning of the slots. That's to only one frame. So no frame is allowed to send in between 9 to 10. So if the frame station wants to send any frame, then it can go only after next slot, that is after 10. Maybe 10 to 11, the next slot. That's to at the beginning. It is something like a student, once the class is started, a student is not allowed to enter into the class. He can allowed only after the completion of the class. Means next hour he can come. That's to at the beginning. If you come again 2 minutes late, gone. You can come only at the next slot. So if you do in this way, there may be chances of controlling the collision. But I am not telling here 100% collisions can be controlled, but still when compared to pure Aloha, you can improve some throughput here, because in pure Aloha, a station can transmit any time between 9 to 10. 9 o'clock one station can transmit, 9:05 one station can transmit, 9:10 another station can transmit, like that. Any station can transmit the data at any time. But here, it is not like that. a station can transmit only at the beginning, that's to one frame at a time. The second frame we can transmit at the next slot. Okay. Hope you understood. So here is the same example. You can see here. See here, slots are there. So first slot, only station 1 has sent the first frame. Station 2 and station 3 both have sent the frame in the second slot. Similarly, station 1 and station 4 has sent the first frame in the slot 3. So like that, frame 2 of station 2 is sent at slot 4. So if you see here, totally same 8 frames are sent overall by 4 stations. But if you see, out of 8 frames, this is the collision duration, only 4 frames are collided. Remaining 4 frames are survived without any collision. Means almost we have achieved some improvement when compared to pure Aloha. Because in pure Aloha, we have seen only 2 frames are survived without collision. But here, almost 4 frames are survived. We have increased some throughput. Okay. So let's see one more example. Same example. So slotted Aloha network transmits 200-bit frames using a shared channel of 200 kbps. Then find the throughput. Same thing. If the station produces 1000 frames per second, 500 frames per second, and 250 frames per second. Same thing. First, you calculate the frame transmission time, which is nothing but 200 by 200, which will get 1 millisecond. So now start doing the same work. So if station is transmitting 1000 frames per second, but our channel speed is working in millisecond, so in 1 millisecond it can transmit up to 1 frame per second. Okay, 1 by 1000. Sorry, 1000 by 1000. 1 frame per second. So now the formula to used in slotted array is G equal to e power minus G. So sorry, 1 second. S is equals to G into e power minus G. But there we are using S is equals to G into e power minus 2G. So here G is nothing but now 1. Just to substitute 1 into E is nothing but Euler's value, which is previously I told you how much. It is 2.718. Just to substitute 2.718 into power minus 1. So if you go on substitute this, you will get up to 0.368%, which is about 36.8% of data or frames are successfully transferred. This means that the throughput will be 365 frames. Means out of 1000 frames, 365 8 frames can successfully survive without any collision. But if you see in this case, in pure Aloha, out of 1000 frames, only 135 frames are successfully transferred or survived without collision. So we have improved a little bit here in case of slotted Aloha. Similarly, we can do for 500 frames per second. Now the load will be 500 by 1000, which is 0.5. Substitute S is equals to G into e power minus G. G is nothing but 0.5. If you do, you will get 30.3%, which is nothing but 151 frames out of 500 will be survived without any collision. Similarly, for 250 frames, we can do 255,000, which is nothing but 1 by 4, which is nothing but 0.25. And just substitute here, G is nothing but 0.25. You will get 19.5%, which is nothing but 49 frames. So out of 250 frames, 49 frames will be successfully survived without any collision. So in this way, when compared to pure Aloha, we are increasing a little bit throughput in case of slotted Aloha. So similarly, this is our random access protocols, what I'm talking. So here the collision rate will be high and the throughput rate will be less. Thereby, we are achieving only less throughput here. So in order to increase, the next we are going to CSMA-CD, carrier sense multiple access. There we can increase another 10 to 15% of throughput. So the more information about that CSMA CD and CSMA CA will be seen in the upcoming lecture. So hope so enjoyed the video. Thanks for watching, and you can subscribe my YouTube channel for more videos. Also, I have uploaded one Udemy course, that is NS3, Network Simulated 3, which is useful for research and education. So the link is available in my description box. So those who are doing research in networking and like a simulation of protocols or any detection, intrusion detection, or any other network related projects what we are doing, these simulations will be more helpful to you. So you can just register to my course and you can get the certification. Okay. Thanks for watching. Meet you in next video. Thank you.